an example of a good function to look at for a more complex example of how to deal with oblique asymptotes. We know that there's going to be an oblique asymptote because the degree of the numerator is one more than the degree of the denominator. Remember, if those two highest exponents are equal, there will be a horizontal asymptote that you would find from dividing their coefficients. And if the degree on top happened to be smaller than the bottom, then that would have a horizontal asymptote of 0, y equals 0. So for this one, we're going to go through all of the work that we would be able to do and all of the information we could get from the function itself. So not looking into the derivatives, but just looking at the function itself. So the first easy thing we are going to look for is the intercepts. So this is going to have x-intercepts at x equals 0, 3, and -4. And the y-intercept, obviously we're putting in a 0 in for our x value, which just gives us 0. So I'm going to flip over to the next slide and we'll graph those. So 0, 3, and -4. Oh, I thought I could zoom in there, but apparently not. So I'm going to put a dot at the 0, a dot at 3, and a dot at -4. And of course, the y-intercept is also one of our x-intercepts, so we don't have to plot that. Okay, then the next thing we're going to look at is vertical asymptotes. Vertical asymptotes, of course, we're looking at where the denominator would be 0. So we have a vertical asymptote at x equals -1 and at x equals 5. So I would go to my graph and I'm going to put in my vertical asymptotes at -1 and +5. And there's that one. So plotting those in as soon as I have them. Now I'm going to flip back again. Now here I would want to go back to my vertical asymptotes and actually double check what's happening around those asymptotes and find the limit. So remember proper limit notation here. The limit as x approaches -1 from the left of f at x. You need to include that function in there. And the limit as x approaches -1 from the right of f at x. And then I'm also going to do the same from the left and right of 5. This is having some troubles with my tablet here. Okay, so here you're just going to use test values. For the -1 from the left, you're going to check, well, what's happening if I sub in, say for instance, -1.1 or -1.01, and see, is that going to a big positive number or a big negative number? Depending how close, how steep the function is and how close of a number you plug in, you may not get a really huge number. So if I plug in -1.1, I get a number around 15, I think, but it's positive, and I know for sure that then that's going to positive infinity. And then likewise for -1 from the right, I would be subbing in something like -0.9, and I get a larger negative number, so that's going to negative infinity. When I put in a number just to the left of 5, so for instance here I would sub in 4.9, I also get a large negative number, so negative infinity. And then if I put in, sorry, that got messed up a bit, and if I put in a large positive number a little to the right of 5, so like 5.1, I get a large positive number, so positive infinity there. Then I'm going to transfer all of this information over to my graph of my function and just kind of show what's going on around those asymptotes that I sketched in. So switching colors here, I know that this is going to go up there towards positive infinity. Here it's going down towards negative infinity, and here as well. And then here it's going up towards positive infinity. Okay. So that's all of the information I've gotten about my vertical asymptotes. I'm going to add another slide in here so I can go through, and I'm going to do the long division, for the oblique asymptote on a separate page. So I have x cubed plus x squared minus 12x plus x squared minus 12x over, forget my function here, x squared minus 4x minus 5. So this is the division that I want to do. So when I'm doing my long division, polynomial division, I have to put the top in here. So x cubed plus x squared minus 12x. And here I'm missing a term. I'm missing my constant term, so I'm going to put plus 0. If you were missing a middle term, like maybe you didn't have an x squared term there, you would have to include a placeholder like a 0x squared. So you have to have every single possible term. If there's not a term in your original expression, you're putting a 0 there. And then here, x squared minus 4x minus 5. So then I'm looking at my leading term here, saying what do I have to multiply x squared by to get to x cubed? And of course, I would have to multiply that by x. So that's going to go in the right column. Like keeping your like terms lined up when you're doing long division is very similar to when you learned long division like in grade 3 or 4 with regular numbers. You had to keep all the ones lined up and all the tens lined up and all the hundreds. So it's like place value, but here it's just like terms. So now we're multiplying this x through to all of those, and I get x cubed minus 4x squared minus 5x. And then I'm going to do subtraction of all of those terms. So x cubed minus x cubed, of course, is 0. That was the whole point. X squared minus negative 4x squared. Careful there with the double negatives, is 5x squared. And 12x minus negative 5x is negative 7x. Oh, not sure what happened there. I think I pushed back by accident. Anyway, now we have to bring down this 0, and that was a 7x, and just add that in as a placeholder. Then we're going to look again and say, hey, what do I multiply x squared by to get this leading term? And of course, I'm going to multiply it by 5. So I put a 5 up top in the constant term column, like the just numbers column, in terms of my like terms. Then multiplying 5 into everything out here. So it's like foiling in that 5 to everybody there. So I would get 5x squared minus 20x minus 25, and then I'm going to do subtraction again to clear out that first term. 5x squared minus 5x squared, of course, is gone. Negative 7x minus negative 20x, so I'm adding 20x, is 13x. And then 0 minus negative 25 is plus 25. So this is my remainder, and this is my quotient. So that's what I get. I'm going to rewrite this function as x plus 5 plus 13x plus 25 over x squared minus 4x minus 5. So this is my remainder, and this is my oblique asymptote. So my oblique asymptote is y equals x plus 5. Because as you go to really, really, really big numbers, if you go anywhere near infinity, this stuff in the brackets, the remainder divided by the denominator, that's going to be 0. That's going to be very, 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 very close to 0. And the actual function will represent, will kind of follow the path of that y equals x plus 5. So I'm going to go over to my function, and I'm going to put on that oblique asymptote. So y equals x plus 5, we're starting at 5. It has a slope of 1, and I am kind of quickly realizing that my scale of my graph is not so great for this, but that's okay. And I am not drawing a super straight line, but we're going to call it good. So this is y equals x plus 5. Label your oblique asymptote. I realized as I was going here, I'm going to have to kind of clean this up, because obviously that, I wish I had started down a little bit lower so I have more space going up high, but that's okay. All right, so here, the last thing I need to do is see how this function is going to be approaching my oblique asymptote. So in this case, I need to figure out what's happening. Am I approaching this from above or from below? So here, we're going to go back and talk about what happens. So the limit as x approaches infinity of this remainder, of this piece here. So as I go to positive infinity, this 13x plus 25 over x squared minus 4x minus 5, this is going to approach 0, but it's going to approach 0 from a positive value. So it's going to be a very, very, very tiny number, very close to 0. And you could get that by subbing in like x equals 100 or x equals 1,000. It's going to be a very tiny number, but it's a tiny positive number. So this tells us that the limit as x approaches infinity of f at x, it's going to equal x plus 5, but from above. This remainder is positive, so it will be added on to the line. So I'm going to go out here and say, as I go close to positive infinity, it's going to approach from above up there. So this is going to kind of go like that. So here, that kind of gives us an idea of what's happening out there. And again, my scale on my graph doesn't allow a lot of detail or a lot of information about what's going on there. We do want to figure out what's going on out here as we go to negative infinity. So just trying to see if I have enough space to really do a good job here. So that is the first one. Likewise, we can sub in, so the limit as x approaches negative infinity of f at x, that's going to be equal to x plus 5 also, but this one's going to be from below. Because we would know that this, you don't actually have to show the step. This is what I want to see. But this, if we had subbed in a very large negative number in here, it's also going to be a teeny tiny answer close to 0, but it will be a very small negative. So it will be subtracted a little bit below this line, y equals x plus 5, it's going to be y equals x plus 5 minus a little bit, so like a little bit below that. So here we're going to be approaching from below. Okay, so we can get a pretty good going through here. We're going up, and then I know I have to go through this point. There's going to be some kind of maximum there. I don't know what it is. We obviously don't have the turning points. There's a turning point there and a turning point there, and then a point of inflection probably there that we would be able to get if we had the other derivatives. So what I'm really looking for, and I'm just gonna kind of go in and highlight in yellow the limit notation that you need to show. So this is important limit notation. This is important limit notation. And the stuff on the previous page about those vertical asymptotes, and then listing your intercepts. So all of the rest of the stuff is like your rough work, but the stuff in yellow, that's what I'm looking for. If that's correct, then I'm going to just kind of glance over your rough work. But what I really need to see for full communication is the stuff that I've circled here in yellow, outlined there, and this kind of notation talking about how you know which way the function is approaching those asymptotes. So I hope that that's helpful. If you have any questions, please email or check in with me.